Yeah, first of all, guys, when we read the question, this question is talking about there is some sort of ordering given. It is saying there are numbers 1 to k, which we have to fill in a matrix of k cross k. And this is telling you row wise what is their ordering. It says 1 is occurring before 2. So that means there is some sort of relationship between 1 and 2. 3 is before 2. So there is some sort of relationship between 3 and 2 also. So if I simply plot this relationship, can I say this is what is representing what row conditions are giving? Is this representing that relationship? 1 is before 2 and 3 is before 2. Yeah. Same way, if we look at column conditions, say it is saying 2 will come before 1 column wise and 3 will come before 2. So 2 is coming before 1 and 3 is coming before 2. So right now I'm just not worrying about what is up down, but this is a row relationship, this is column relationships. So first intuition, when we see problems where some sort of ordering and relationship is given, ideally we can draw the relationships in a format, and this format is giving us a hint. This problem might be modeled as a, this problem can be modeled as a which topic problem? Yeah, graph problem. So there are some sort of relationships we are representing. So let's try to visualize, okay, if we have a graph, what is this problem asking us to do? Now, yeah, people who are aware of graph, people who have learned about graph, they would kind of quickly reach the intuition that this is asking you to extract some sort of order. And that order, if you have a directed graph, in directed graph, if you start with the first element which does not have any dependency, print that it is 3. Then you go to the next element, because after 3 is done, treat these arrows are like 3 has to be visited before 2, 2 has to be visited before 1. So this order of traversing the nodes of a graph by taking care of dependencies, there is a name for that order. That name is called topological sort. And there is a standard algorithm for printing the topological sort of a graph. So this graph's topological sort is 3, 2, 1. Let's come to the left side, which is a row graph, row dependencies wise. What do you think is topological sort for left side? What node we can print first? I said we will start with a node which doesn't have any dependency. So 1 doesn't have any dependency, so we can go with 1 first. Now after 1, can I print 2? Are all the dependencies before 2 are taken care? No. So 2 cannot be done until unless 3 is done. So 1, 3, 2. This is one topological sort. And we are aware that topological sorts for a graph can be multiple. This is a valid topological sort. That means if you visit the nodes 1, 3, 2, you're not violating the order. And same way, another topological sort will be, you can go 1 later, 3 first, because 3 doesn't have a dependency. Go with 3 first, then go with 1, and then go with 2. So we have 2 topological sorts possible. Now for now, just pay attention. Let's say if we have topological sorts available to us, for now we will pay attention to one topological sort here and one topological sort here, and we will try to make some conclusion, draw some conclusion. Can we utilize this information to fill the matrix? So this is index 0, this is index 1, and this is index 2. Okay, wait. This is index 2, this is index 1. This is index 0, this is index 1, this is index 2. Now we will use these 2 arrays to try to fill our matrices. So left side is talking about row number, right side is talking about column number. So now if I ask you, where should 1 be filled? Look at both these arrays. This is giving you some row indices. This is giving you column indices. According to this, tell me where we should fill the 1 in the matrix. We could use the index of individual arrays as 2D indices. What do you mean by that, Shashank? Can you unmute and speak?
Yeah, I see that 1 can be kept at 0 and 2. Okay, that's wrong.
Okay, so if I ask you, For 1, tell me which row 1 should go to, which column should 1 go to. Left side was telling you row ordering. So can I say 1 is stored at index 0 and here 1 is stored at index 2. So can I say 1 is okay to store at 0th row and second column? Do we all agree with? Okay. So let's take a matrix and we are trying to fill the matrix. We are saying 1 will go to 0th row and second column. So let's take a matrix and go and fill the matrix 0, 2. So I am going and filling 1, utilizing the information into arrays that we got. Now, same way, where should 2 be filled? 2 is at index 2 here. 2 is at index 1 here. Where should we fill 2? It is at 2, 1. Go to second row, first column. So 0, 1, 2. Second row, first column, let's go and fill 2. Same way, where should 3 be filled? 3 should be filled in first row, 0th column. So first row is this, 0th column is this. Now this is one possible answer. If I ask you this filling, although here the output is different, which they are expecting, but if I ask you, is this filling, is this output meeting the criteria of row conditions? 1 is above 2 and 3 is also above 2. Yes, 1 is above 2, 3 is also above 2. Let's see column wise. 2 is before 1 and 3 is before 2. 2 is before 1 and 3 is before 2. So this is also meeting the criteria. So this solution is a valid solution because there were 2 topological sort. This will work. If we would have considered the second topological sort, if we would have taken that topological sort, we have one more solution to the same problem. Let's see, using second, what answer do we get? Using this and this, tell me where should 1 go? Which row and which column should 1 go to? 1 should be stored at 1, 2 because it is at first row and second column. So first row, second column is this 1. Okay, where should 2 go? 2 should go to 2, 1 because it is at second index in row array, first index. So it is 2, 1, that is this. And where should 3 go? Here also 3 is at 0. Here is also 3 at 0. So this is second answer. So ideally, we had to fill the array matrix and return. Any of these would have served the purpose. Both solutions will get accepted. And now coming to the crux, coming to the point, how do we get the topological sort of a given graph? So how many people are not aware, not comfortable about topological sort? Can I have responses in the chat? Okay, so I'll try to give you a context and idea about it. It's very easy. If you know how to use Q, then it is very simple. Okay, so let's take a look at that. So for now, I'm parking this here and I'm saying, if you get these 2 arrays, you can fill the matrix easily. Is that assumption okay? If we can somehow get 2 arrays, call it row topological sort, call it column topological sort, then rest of the problem we can solve. Okay, so let's build the context before that. So first idea we are saying, get row top sort. Row topological sort will be an array, remember that. So I'm calling it as like a pseudo code. It is list of int row topological sort and column topological sort. We need a way to get these. So get topological sorts. And after getting the topological sort, let's kind of summarize what we said here. We said, where is 1 located? 1 is located at index 0 in row number, at index 2 in column number. Now we are searching. If we have to search for 1, it will take a long time. We can build a reverse index. We can say 1 is stored at index 0. So can I say, can I build a map of int comma int? For each value, we are going to store row index and column index. So think it like this. So I'm going to say, when I get this topological sort array, I will take 1 is stored at index 0. I will store that in row index. That 1 is the key and value is 0. So all I'm doing is I'm just storing the reverse map 1, 0, 3, 1 and 2, 2. But array stores it in a different way. Okay, so we will build this map, and after building this map, using map, fill the matrix. This part is clear. Only thing we have to figure out is how do we get the topological sort? Let's talk about that. So for topological sort, I will be taking a separate graph and we will come to that. Let me take a graph which is having 2 in the beginning. 2 is taking an arrow to 1. Let's say 1 is going to 3. And then 1 is also going to go to 4. And 4 will come to 3 again. For this graph, help me with the topological sort. What will be the topological sort of this graph? Okay, Vamshi, you have a typing mistake. Okay, yeah. So we all are saying topological sort is going to be 2, 1, 4, 3. Okay. For 2, 1, 4, 3 topological sort, if I ask you, why did you start with 2? What was special about 2? What is special about 2? It is independent. It does not have any incoming edges to it, which is called in degree in a graph. So if I ask you, let's build an array, somehow we will build an array of in degrees. And I want to store in degree of each element. How much is the in degree of vertex 1? How many edges are incoming to vertex 1? There is 1 edge incoming. How many edges are incoming to vertex number 2? Vertex number 2 is 0. How many edges are incoming to vertex number 3? 3 has 2 edges incoming. And how many edges are incoming to vertex number 4? There is 1 edge incoming. If we somehow build this array, from this array, choosing the first vertex where we are starting topological sort is easy. That vertex is vertex number 2, whose in degree is 0. Okay, so we take for topological sort. First of all, build in degree array. We will figure out how to build the in degree array. Second, take a queue and say for every vertex with in degree 0, put that vertex in queue. Q dot push, put that vertex whose in degree is 0. So our queue so far will have which vertex in the queue? 2 will go into the queue. Okay. Now we will do a standard procedure. We will keep processing until unless queue becomes empty. So we will say while our queue is not empty, we will do certain steps. We will take the first value out of the queue, q dot front and q dot pop. I'm treating queue has 2 separate functions. Front only returns top value, and let's say pop is going to remove. Pop removes front value. So what we have essentially done is we have removed 2. After removing 2, 2 can be printed for topological sort. Now tell me, if 2 is going away, if 2 is done, which vertex has its dependency reduced? Which vertex has dependency reduced? That is 1. So from 2, we will figure out whichever vertices are reachable, we will go and decrement their in degree by 1. We will say, hey, your in degree becomes 0. So here we do one more thing. For every vertex adjacent to, for neighbor of x in, let's say, adjacent vertices of x, we will talk about what adjacent of x is. We are going for every neighboring vertex and we are saying in degree of that neighbor vertex is minus minus. So we have just gone and reduced the dependency of 1 by this. If in degree of 1 has become 0, what does it mean? Can 1 be the next element which we have to print? Yes. So we push that into the queue. So this is if in degree of nx is 0, we say, let's say q dot push of x. We push a vertex in the queue only if its in degree becomes 0. Okay, so now vertex number 1 will become in the queue. This is the whole procedure. That's all. We will keep repeating it. Let's see what happens. Now 1 will come out of the queue because queue is not empty. We will remove 1. So 1 comes out. We will print 1. After printing 1, what will we do? 1 is out of the queue. 1 is printed. Let's say print x. 1 is printed. Now we have to go over all the neighbors of 1. Who are the neighbors of 1? From this graph, who are the neighbors of 1? It is 4 and 3. Let's go to 3, reduce its in degree by 1. Its in degree becomes 0. Oh, sorry, in degree becomes 1. Should we put 3 into the queue? No, because its in degree is still not 0. So we will not put 3 into the queue. 4's in degree also reduces by 0. Reduces to 0. Should we put 4 into the queue? Yes. So 4 goes into the queue. And this is what we are doing. For every neighbor of 1, we have reduced the in degree, and whichever vertices became in degree 0, we put them into the queue. Okay. So now our queue has 4. Queue is not yet empty. Take 4 out. Print 4. After printing 4, what we should do? After printing 4, what we should do? We should look at the neighbors of 4. Who are the neighbors of 4? From 4, where we can go? We can go to 3. 3 is in degree. We will reduce from 1 to 0. Since the in degree of 3 became 0, we'll put 3 into the queue. Okay. Now you will go up again. Queue is not empty. Take 3 out. Print 3. 3 does not have any outgoing edge. There are no vertices, no neighbors. So this while loop will complete. And we come out from here. And this printing part that we were talking about, let's say list of int top sort. Let's say we are taking another vector, another list, and we are adding to that. Rather than printing, we are saying topological sort dot append, just using a pseudo function name, not going language specific. So we are going to, rather than printing, we are going to put it in array, and that's the array we are returning top sort. So if we write this as a separate function, as a separate procedure, this will give us the topological sort starting with a given vertex, which is having in degree 0. Yeah, guys, are we clear? Okay, so we have to call this topological sort function 2 times, and we have to pass it a graph also. Of course, this adjacency thing that we were talking about, from original relationships, yeah, from these relationships, we will have to build a list of lists. So graph will be represented as a list of list. Graph will be a list of int, where this is our graph. G of I contains all the neighbors of vertex I. That means if I ask you here 2, if you see 1, 2, 3, 4, index 0 we will ignore. Index 0 will not have any list. This will have an empty list. Index 1, who are the neighbors of 1? From this graph, who are the neighbors of 1? 3 and 4. We will store that in 1's list. Who are the neighbors of 2? 2 has neighbor only 1. Who is the neighbor of 3? None. That's it. So this is our graph. Where did I? Okay, 4 also I missed. 4 has a neighbor 3. Okay, this is our graph, which is a list of lists, which is a vector of vector, and we will be using that. If you see here, when I was looking at give me the neighbors of 1, we have to go in that adjacency list. This is called, let's call adjacency list. And we were using that here. So if we can convert our given graph in a 2D format, then we can pass that graph here, that adjacency list to topological sort function, adj list, which is a list of lists. And this function will be capable of returning us a list of int. And this is list of int. Yeah, so this is overall thing about topological sort. Now, one last point remaining about this is, help me visualize this topological sort. If I give you a graph, let's say you have 1, then you have 2, then you have 3, then you have 4 here, and let's say from 4 we are going to 2. Let's first build the in degree array. What will be the in degree array? What is the in degree of 1? How many edges are incoming to 1? It is 0. What is the in degree of 2? 2 is 2. What is the in degree of 3? In degree of 3 is 1. What is the in degree of 4? 4 is 1. Okay. So this is the graph now. In queue, what will you put? You have calculated in degree. Your starting point wise, what will you put into the queue? You will put 1 into the queue because it's in degree 0. Okay. Now 1 comes out of the queue. You print 1. After that, what do you do? 1 is printed. Now what should we do? See, when we were taking vertex out, we were going to its neighbors. Neighbor of 1 is 2. Go to 2 and decrement its in degree. Its in degree becomes 1. Shall I put 2 into the queue? No, we cannot put because its in degree did not reduce to 0. So nothing gets put into the queue. Queue becomes empty and we come out. That means topological sort completed, but our array that we were getting, in this array, how many elements got added? In topological sort, how many elements got added? 1. This is one more application of this algo. It says, if your while loop completes without putting every vertex into the array, without printing every vertex, that means graph has a cycle. If you see there is a cycle, 3 cannot be done before 2, 4 cannot be done before 3, and 2 cannot be done before 4. So there is a cyclic dependency. This is a cycle detection part of this algo. So can I say that topological sort will still work on a cyclic graph, but this array will not have total elements returned to us. And that is the beauty here. So when we got topological sort of row topological sort, can I say row top sort is equal to get topological sort of the graph adjacency list? Can I check here if row top sort dot size, what will be the check you will put? If row topological sort size, how many elements should have been there in topological sort? Yeah, there should be k elements according to the problem. We are talking about k vertices here, 1 to k numbers. If this size is less than k, you can simply return empty matrix. That is what the question talked about. There was one thing, it said that if you do not find, if no answer exists, return an empty matrix. So that is a check that we will have to put. And same way, you will get a topological sort for column. If column topological sort has a cycle, we will do the same thing. Get topological sort of adjacency list. If column topological sort dot size is less than k, then also we will return empty matrix. It's just like declare the matrix and return. Otherwise, we can use the map approach and filling this. Now, last thing that is remaining is creating row adjacency list and column adjacency list. Those are the two lists of lists we have to create as a graph. List of int. And this should be row adjacency list we are passing. That is one graph. Column adjacency list is another graph. Now, the last point is how do we convert the given input to reading this, can we create an adjacency matrix? Yeah, guys, reading this, can we create adjacency matrix? Yes. So you take a matrix of k plus 1 size, k plus 1 rows should be there. Go to first row, push back 2. Go to third row, push 2. So then you will start gradually building your adjacency matrix. Same way, based on column conditions, you will create a graph. So ultimately, this representation is what we are going to create. So it's like build them using whatever inputs were given to us. Inputs were using row conditions and column conditions. Yep, so that is what we have to do. Now, if you want a quick walkthrough, I can show you the code. I think this may be more cluttered code during the contest that I have written. But if you see, started with taking a row graph and column graph. So I'm creating graph. And in degrees, I created at the same time so that later on, we don't have to worry about creating in degrees. So now going to row conditions. Row conditions are these row relationships that 1 is coming before 2 in row wise. So 1 is P0, 2 is P1. So from in 1, I'm pushing 2 and I'm counting 2's in degrees plus plus. So this is row conditions is helping me create a graph as well as in degree array. Second is using column conditions, creating a column graph and its in degree array. These two are done. Now what we are doing is taking row topological sort by calling the function. What am I doing in this function is I'm passing in degree array also, I'm passing k also. So taking a queue, whichever vertices have in degree 0, push them into the queue, take an answer vector. And now while queue is not empty, take the element, push back into the answer. For every neighbor, reduce the in degree. If in degree is 0, just push it to the queue. And in the end, return this answer. Now this topological sort function is called twice. First time I call this topological sort, I figure out if the size of this array is less than k, then return the matrix. It is empty. So far, nothing is filled in the matrix. Same way, if column topological sort is less than k size, return the matrix as it is. Okay, this was, I think, for debugging purpose. I'm commenting it out. Now I created two maps, row map and column map, going over the array and saying index is the key and value. 1 is found at index 0, 2 is found at index 2, and so on. So building two maps here, then resizing the matrix to k cross k, and just using row map and column map, filling it back in matrix at whichever row index and column index. We should put the value 1, 2, 3, 4, 5, putting that and returning that. Okay. Yeah, and especially people who are doing topological sort for the first time, I will strongly recommend you to take a look at topological sort in Leetcode. At least if you have understood the discussion, I said you should solve one prerequisite problem that will prepare you better for future contests. It's a course schedule problem. I'm pasting the link in the chat here. So this will strengthen the learning that you have got. So this is asking you to detect something. And if you are interested, more enthusiastic in solving more problems, there are total 30 problems on Leetcode on topological sort. And you can kind of solve more problems from here. And all of them are categorized into medium hard. And it's a good topic. It will take time, but I will say it will be worth spending time on this topic. It will prepare you better for future contests if you see any problem on topological sort again. Any questions from anyone? Okay, how many of you attempted this problem during the contest? Or how many of you reached the idea that I can model it as a graph problem and it will take topological sort? Okay. Cool. So you all know that there is some work to be done on this side. And topological sort, one algorithm we have talked about, this is called Kahn's algorithm. And this should be like practice it 2-3 times. And this is very easy. Just a simple application of Q. Okay. Cool, then I think we are good for today. I hope you found this session useful, informative. Thank you, Kaushik, for taking up the initiative and covering first 3 problems.
Most welcome, sir.
Yeah. Yeah, and thank you everyone who have come here. I appreciate your enthusiasm towards coding. Yeah, have a happy Sunday. We'll close it here.